Hello everyone, welcome to the video lecture of this course Finite Element Method. So this is the fourth module that we are continuing, and this module basically deals with the two-dimensional vector variable problems. So earlier in this module we have discussed the elasticity equations, and there we have seen four basic sets of the elasticity equations. So based on those elasticity equations we have discussed several numericals. Next, the concept of the axisymmetric elements were discussed in details, and based on the different formula of these axisymmetric elements we have discussed a lot of numericals. Now regarding these axisymmetric elements we have seen the formula for the shape function, then the stress strain relationship matrix, then strain displacement matrix, then the stiffness matrix. So all these things we have discussed earlier, and based on this different terminology we have discussed several numericals, and those numericals were a bit lengthy, and a lot of matrix operation like matrix multiplication mainly it was required. So different numericals were discussed earlier based on the concept of the axisymmetric elements in this module. Now today in this lecture we will discuss the concept of the plate element, the thick plate theory, thin plate theory. All these things will be discussed in details in the next lectures, but today we will discuss regarding the thin plate theory in details. Okay, so what is this thin plate theory, what are the sign convention, and how to calculate the moment and the forces for this thin plate theory, then what are the boundary conditions that we need to consider. So all these things will be discussed in details in this lecture today. Okay, so let us start this lecture. So these are the course objectives and course outcomes of this subject finite element method, and these are already known to us. So I will just skip these slides, and next this slide known as the COPO mapping we can see for this course finite element method. I will also skip this part because this COPO and the mapping of this course outcome and program outcome it is already known to us. So we will start from this slide, that is the concept of the plate theory. So the aim of the plate theory it is actually to calculate the deformation and stresses in a plate subjected to loads. So this is the aim of this plate theory. So first actually we need to know what is this plate. We are going to discuss regarding the plate theory, but we need to first discuss, or we need to know first, that what is this plate. This plate is actually a planar structure with a very small thickness compared to the planar dimensions. Okay, this plate it is actually a planar structure with a very small thickness in comparison to the planar dimensions. Now the forces which are applied on a plate are perpendicular to the plane of the plate. So therefore the plate resists the applied load by means of bending in two directions and twisting moment. So the bending, twisting, all these concepts are known to us. So what happens when a force or the forces are applied on a plate, these are actually perpendicular to the plane of the plate, and in that case the plate resists those applied forces by means of bending in two directions and the twisting moment. So these are the characteristics of the plate. what happens when some forces are applied, how the plate resists those applied forces. Now the plate theory, it takes the advantage of this disparity in length scale to reduce the full three-dimensional solid mechanics problem to a two-dimensional problem. So this is the aim of the plate theory. It is to calculate the deformation and the stresses in a plate subjected to loads. So concept of the stress, deformation, strain, all these things are already known to us. So when some loads are being applied to a plate, then what is the stress that is generated inside the element, then the amount of deformation, all calculation of all these things are the main aim of the plate theory. Now a flat plate, like a straight beam, it carries the lateral load by bending, and the analysis of the plates are categorized into two types, which is based on thickness to breadth ratio. So what are those two types of plate analysis? These are actually thick plate and thin plate analysis. So how to classify, how to identify which plate are thick and which are thin? So we need to remember for that if the thickness to width ratio of the plate is less than 0.1 and the maximum deflection is less than 1/10 of thickness, in that case the plate is classified as thin plate. Let me repeat that again. The concept of the thin plate, how to classify which the plate is thick or thin. So this is actually based on the thickness to breadth ratio, this thick or thin concept. So if the thickness to breadth or width ratio of the plate is less than 0.1 and the maximum deflection is less than 1/10 of thickness, in that case the plate is classified or identified as the thin plate. And the well known Kirchhoff's plate theory, it is used for the analysis of the thin plate. But in case of the thick plate, we use the Mendlin plate theory. And that case, that means in case of the thick plate, the effect of shear deformation is included. So these are the different theory that is applicable in case of the thin and thick plate. In case of thin plate, we use the Kirchhoff's plate theory, and in case of the thick plate, we use the Mendlin plate theory, where the shear deformation is included. So these are the concept of the plate theory. So here what we have seen, the aim of the plate theory is to calculate the deformation and stresses in a plate subjected to loads. And the analysis of the plates are categorized into two types, and which is based on the thickness to width or breadth ratio, and it is categorized as thick and thin plate analysis. Now, if the thickness to width ratio of the plate it is less than 0.1 and the maximum deflection is less than 1/10 of thickness, in that case the plate is classified as the thin plate. So today in this lecture we will discuss in details the thin plate theory, and in the next lecture we will discuss the thick plate theory. So let us move to the next slide. Now we will discuss the notations and the sign conventions that we use in case of this plate theory. So in the figure given 4.6, the notations and sign conventions we can see. So let us consider plates to be placed in XY plane, the representation of plate surface slopes Wx, Wy by right hand rule produces arrows that point in negative y and positive x direction respectively. So both surface slopes and rotations are required for plate elements. So the signs and subscripts of rotations and slopes are reconciled by replacing theta x by psi y and theta y by minus psi x. So in this diagram we can see the rotations of meet surface normal, where the theta x is psi y and theta y is minus psi x. And in case of the slopes of plate surfaces, Wx is del W del x and Wy is del W del y. So these are the concept of the notations and sign conventions which are used in case of the plate theory. So let us move to the next slide where we will discuss the thin plate theory in details. So what we have seen earlier and what we have discussed earlier in the introduction part of this plate theory, that in case of the thin plate theory, the widely used law, it is the Kirchhoff's law. The Mindlin or the Kirchhoff's plate theory it is actually, and it is Kirchhoff's theory, it is applicable for the thin plate. So in this diagram you can see the Kirchhoff's plate after bending. So what is seen that the classical thin plate theory, it is actually based upon the assumptions initiated for beams by Bernoulli, but first applied to plates and shells by Love and Kirchhoffs. So they have firstly applied the assumptions in case of this thin plate theory. So this theory is known as the Kirchhoff's plate theory, which is applicable to the thin plate. Now there are certain assumptions, and there are actually three assumptions which are used to reduce the equations of three-dimensional theory of elasticity to two dimensions. So what are the three assumptions in case of this Kirchhoff's plate theory? The first assumption that we consider, that is the line normal to the neutral axis before bending remains straight after bending. Okay, so this is the first assumption, that is the line normal to the neutral axis before bending remains straight after bending. So this is the first assumption. The second assumption is that the normal stress in thickness direction is neglected. That is the sigma z equals to 0, that is neglected here. And this assumption actually converts the 3D problem into a 2D problem, because we are neglecting the z sigma z equals to 0, that is in case of z direction we are neglecting the thickness. And in case of the third assumption, it is the transverse shearing strains are assumed to be 0, that is the shear strains gamma xz and gamma yz will be 0. So the thickness of the plate does not change during bending. Okay, so these are the three assumptions which are considered in case of the Kirchhoff's plate, and using these assumptions we can convert the three-dimensional problem into a two-dimensional problem. So let us again discuss this part, that is there are certain assumptions in case of the thin plate theory, and based on those assumptions we convert the three-dimensional theory of elasticity into two-dimensional problem. So these concepts, these are actually used in case of the Kirchhoff's plate theory, Kirchhoff's thin plate theory. And the first assumption is actually the line normal to the neutral axis before the bending remains straight after the bending. So here you can see the line which is normal to the neutral axis, and before and after bending these lines are straight. In this diagram you can see the first assumption. Next, the second assumption is that the normal stress in thickness direction is neglected. That is sigma z is 0, and this assumption actually converts the three-dimensional problem into two-dimensional problem. And the last and the third assumption is that the transverse shearing strains, these are assumed to be 0. So that means the shear strain gamma xz and gamma yz, these will be 0. And thus the thickness of the plate does not change during the bending. In this diagram also you can see the thickness of the plate, it is not changed. It is the same before and after the bending. So let us move to the next slide. Now we will discuss different relationship in terms of the different equations for this thin plate element. So in the figure 4.8 you can see a thin plate element. So let us consider a plate of thickness T has mid surface at a distance T by 2 from each lateral surface. Now for the analysis purpose, xy plane is located in the plate mid surface. Therefore, z equals to 0 identifies the mid surface. Let u, v, w be the displacements at any point x, y, z. So these are the things that we have considered for this thin plate element. So the variation of u and v across the thickness can be expressed in terms of displacement w as u equals to minus z del w del x and v equals to minus z del w del y. So this is our equation number 4.51. Now w is the deflection of the middle plane of the plate in the z direction. Now the relationship between the strain and deflection, it is actually represented as epsilon x, this is equals to del u del x, this is equals to minus z del 2 w del x2, this is equals to lambda suffix x multiplied by z. This is the equation number 4.52, and it is the relationship between the strain and deflection. Next, epsilon y, this is equals to del u del y. So this is equals to minus z del 2 w del y2. This is equals to lambda yz, and the gamma xy, which is the shear strain, this is equals to del u del y plus del v del x. So this is equals to minus 2 lambda xyz. So these are the three equations which reflects the relationship between the strain and deflection. In these equations, epsilon, it corresponds to direct strain, then gamma corresponds to shear strain, and lambda corresponds to curvature along respective directions. Now if we write this above three equations in matrix form, then we can write that a column matrix of epsilon x, epsilon y and gamma xy, this is equals to minus z multiplied by a column matrix which consists of del to w del x2, del to w del y2, to del to w del x del y. So this is our equation number 4.55, which represents the relationship in between the strain and deflection. This is the relationship in between direct strain, shear strain and the curvature along the respective directions with the deflections. So these are the basic relationships of thin plate element. Next we will see the constitutive equations. So the concept of these constitutive equations we have discussed earlier while discussing the four basic sets of the elasticity equations. Now the Hooke's law, it is also known to all of us that the stress is proportional to strain within the elastic limit, and from that we have got one constant of proportionality, that is Young's modulus. So from Hooke's law we can write that sigma vector, that is stress, this is equals to d matrix multiplied by the epsilon, that is the strain. Now this constant of proportionality d, this is equals to e by 1 minus nu square multiplied by 3 by 3 matrix. So which is our equation number 4.57. So here d matrix, it consists of the Young's modulus and Poisson's ratio. So this matrix, it is also familiar to us, and we have used this matrix to solve different numericals earlier. Hence d is equal to the value defined for 2D solids in plane stress condition, that is sigma z equals to 0. Next we will discuss different formula to calculate moments and shear forces. And let us consider a plate element of dx dy and with thickness t. It is the area is dx dy and the volume will be t dx dy. The plate is subjected to external uniformly distributed load P, and for a thin plate, body force of the plate can be converted to an equivalent load. Now from Hooke's law, we can write that sigma vector, that is the stress, this is d matrix multiplied by the strain matrix. In this formula we have seen earlier in the constitutive equations. So that means sigma equals to minus z into d into del w, because the epsilon, that is strain, this is minus z into del w. Now from the above relation it is seen that the normal stresses are varying linearly along the thickness of the plate, and so the moments on the cross section can be calculated by using this relation, that is m equals to a column matrix of mx, my and mxy. This is equals to integration minus t by 2 to t by 2. This is equals to sigma z dt. So this is our equation number 4.59. So in this relation and in this diagram also we can see the forces and moments in plate. It is given here in the first diagram. It shows the stresses in the plate. This is the sigma xx, then sigma xy, then sigma xz, sigma yx, sigma y, all the stresses are shown here along the x and y directions. And in case of the forces and moments in plate, the moment mx, my, mz, all these are also represented here. If we substitute the equation 4.58 in equation number 4.59, so equation number 4.58 was this one, sigma equals to minus z d and del w. In equation number 4.59 it was the representation of the moments. So we will now substitute the equation 4.58 in equation number 4.59. So that means it will be now minus integration minus t by 2 to t by 2 z square dt multiplied by d matrix into del w. That means the column matrix of the moments, that is mx, my and mxy, this is equals to minus t cube by 12 to d matrix multiplied by delta w. This is our equation number 4.61. Now on expansion of the equation 4.61, we can find that mx equals to minus 80 cube by 12 into 1 minus nu square multiplied by del 2 w del x square plus nu del 2 w del y square, that is dp equals dp multiplied by lambda x plus nu lambda y. So this is our equation number 4.62. So different steps have been skipped here to get the equation 4.62 from the equation number 4.61, and the value of my, it is also represented here as equation number 4.63, that is dp multiplied by lambda y plus nu lambda x, and the value of mxy, it is given here in equation number 4.64, which is minus dp into 1 minus nu by 2 into lambda xy. Now this dp, it is the flexural rigidity of the plate, that is et cube divided by 12 into 1 minus nu square. So this is our equation number 4.65. Now if we consider the bending moments which varies along the length and breadth of the plate as a function of x and y, then if mx acts on one side of the elements, we can write mx equals to mx plus del mx by del x into dx, which acts on the opposite side. So this concept on the representation of any parameter in the two different sides of an element is familiar, known to us. Now the equilibrium of the plate element, that is del qx del x plus del qy del y plus p, this is equals to 0. Then del mx del x plus del mxy del y, this is equals to qx, and del mxy del x plus del my del y, this is equal to qy. So these are the equations which are applicable for the equilibrium of the plate element. Now using these equations, and after the rearrangement, we will get the value of qx, this is minus dp del x into lambda x plus lambda y, that is qx equals to minus dp del x to del 2w del x2 plus del 2w del y2, which is equation number 4.70. And in this similar manner, we are getting qy as equation number 4.72. And finally we are getting the equation as minus p by dp, this is equals to del 4w del x4 plus 2 del 4w del x2 del y2 plus del 4w del y4. So this is the equation number 4.73. So these are the calculation in case of the thin plate theory for the moments and the shear forces. Now what are the boundary conditions that will act. So for different boundary conditions of the plate, suitable conditions are to be incorporated in plate equation for solving the governing differential equations. Now, as an example, there are different conditions which are given here that need to satisfy along y direction of the plate for various boundaries. In the figure, you can see the plate with 4 boundaries are given, and along y direction for simply support edge wxy equals to 0, mx equals to 0, where x is constant and 0 less than equals to y less than equals to b. Next, the number 2 boundary condition, it is for clamped edge along y direction wxy equals to 0, del w del x for xy, this is equals to 0, where also x equals to constant and 0 less than equals to y less than equals to b. And for free edge along y direction mx equals to 0 and qx plus del mxy del x, this is equals to 0, where x equals to constant and 0 less than equals to y less than equals to b. So these are the 3 different boundary conditions which are applicable along y direction, but for 3 different cases, which are simply support edge, clamped edge and free edge. Now similar to this above, the boundary conditions along x direction can also be obtained, and once the displacement wxy of the plate at various positions are found, then the strains, stresses and the moments developed in the plate can be determined by using the corresponding equations. So these are the concept of the plate theory, and basically the thin plate theory that we have discussed in this lecture. And regarding the thin plate theory, we have seen the Kirchhoff's plate theory for bending and the 3 different assumptions that are considered to convert the 3-dimensional element into 2-dimensional element. And regarding this plate theory, we have seen the sign convention, then the constitutive equations, and how to calculate the moments and shear forces, how to consider the boundary conditions. All these things regarding this thin plate theory are discussed in details in this lecture. So this is the end for this lecture, and in the next lecture we will discuss the thick plate theory, where we have seen the Mendelian theory, it is actually applicable for the thick plate theory. So this concept will be discussed in the next lecture, and different small questions regarding these different modules that we have studied till now will be discussed in details.